A square is possible. Giving an equation of a square, however, is something that would require actually 4 different equations, one for each line, and so that's not something I would use in a problem. What about another shape?
A circle?
What about a circle? And specifically, where would that circle have to be located?
On the origin.
It's got to be where the center is at the origin. So look at this example. What do you think about that shape? Is it symmetric to the origin?
Yeah.
When you spin it, obviously, when you spin it, it still looks like a circle all the time, right? If you fold it on the x-axis, does the top part land on the bottom? When you fold it on the y-axis, does the left side fall on the right side? When you fold it on this line right here, do the 2 sides come together? When you fold it on this line, you see what I'm saying? So, yes, a circle is a shape that could have all yeses, if its center was the origin.
So that wouldn't be a function of a circle.
A circle is not a function, though. Why not?
Because it's symmetric to the y-axis and the origin.
Okay, but before you even knew about that, why is a circle not a function from old knowledge that you had back in Algebra 2 and Advanced Math?
It's not a line.
Well, lines aren't the only functions. Parabolas can be functions, certain parabolas. How did you test a graph in the past to see if it was a function or not? The vertical line test. Does a circle pass a vertical line test? If you do this, how many times does the vertical line touch a circle? 2 times. And which means what? It's not a function. Okay? All right. But again, that's really not your problem. Okay? That's going to be my problem to know in advance whether the problem I'm giving you is a function or not. And I'll have to, be alert to that. All right. Let's go back to our families of functions then. Okay? Now, remember yesterday I started off by making sure we were clear we knew what a function was, so that we didn't have to have any fear, any misgivings about dealing with these families of functions, okay? And they're nothing more than a group of ordered pairs where every x has only one y. Isn't that the way it works? Okay. Now, we want to look at the various families. If you have your textbooks with you again, go ahead and open it, because the textbook does some nice graph work in drawing an example of each family, and so we'll go ahead and use it.
We need to know the identity function and constant function.
We're not going to worry about those, because those two are actually just lines, and linear functions you did in Algebra 1. So we're not going to do any problems in this section that are pure lines. The simplest shape we're going to start with is right here, the quadratic functions, okay? Matter of fact, what I'm going to do, watch. You see where I wrote linear functions yesterday? I'm going to put an X through that, because we're not going to deal with that family. It's a valid family, okay? The linear function family, very valid family. But you did linear functions in Algebra 1, and you did a little more of them in Algebra 2. We're not doing them in Precalculus. So our first family is called the quadratic family. You recognize it because of the x having an exponent of what number? 2. Okay. Now, In each family, there is an equation called the parent equation. The parent equation. Just like in our real families, we have parents, okay? The parent equation in these families is always the simplest equation of all. So y equals x squared is the parent of the quadratic family. It's got the x squared, which it has to have if it's going to be in the quadratic family. What's the coefficient of x squared in this equation? The coefficient.
1.
Where's that?
1.
1. Where is the coefficient? Billy, where is it?
In front of the variable.
It's in front of the variable. There's a coefficient right here of 1. You can't get a simpler coefficient than a 1. So this equation is the parent equation for the quadratic family. And what you're looking at, the parabola that you're looking at up there or in your book, I'm trying to basically redraw what's in your book. I don't do as good a job as the book does, but you get the basic idea here. This parent equation, this equation goes with this parent graph. They go together. Okay? Now, every family that we're going to deal with in this section has a parent. So the first thing I want to do is just go through each family, give you its name, give you its parent equation, and show you the graph of that parent equation. Okay? So our first family is quadratic. Our second family that we're going to be working with is going to be the cubic family. So we have cubic functions. Now, the equation, okay, first of all, what makes a function called cubic? Why do we give it that name? What are you looking for so you'll know when you have cubic? Anybody want to guess?
The x is cubed.
The x is cubed. So if I write an equation that basically has just that in it, y equals x cubed, that's my parent equation for this family. You can't get any simpler than y equals x cubed, right? Okay. Now, the graph of a cubic equation, I think, is a real cute little shape. Okay? It looks like this. It comes up from down low in the third quadrant. And I don't know why this word is what comes to my mind every time I draw this little graph, but squiggle is the word that comes to my mind. It like squiggles through the origin, okay? Makes that little curve, like squiggle through the origin. So, in this class, okay, you know, I probably will refer to this kind of a shape as a squiggly, okay? This is not a mathematical term you'll find in any math textbook, but when you hear me use that word, you're going to picture a graph that looks like this, okay? It comes up and then does that little squiggle somewhere. Now, the parent squiggles through the origin, but other squigglies might be squiggling someplace else, okay? Now, one thing I want you to understand, okay, if you look at the graph here, watch me point, okay? See this piece of the graph right here? This part of the graph